All right, let's get right into it. Welcome to this step-by-step explainer on mastering variable frequency drive, or VFD, installation and commissioning. Now, if you're an automation engineer, a maintenance tech, or a PLC programmer, you already know that these drives are literally the beating heart of modern industrial control. But today, we aren't just going to talk about what a VFD does. Instead, we're breaking down exactly how to install and commission one perfectly, safely, and strictly to factory standards.
So let's start with a quick reality check. What actually happens if a VFD is not installed correctly? Well, the stakes are incredibly high. We're talking about sudden motor faults, catastrophic drive damage, frequent nuisance trips that completely halt production, and of course, astronomical maintenance costs. Proper installation really isn't just a best practice, it's the absolute foundation for safe, long-term operation. A single corner cut today is going to be a massive headache tomorrow.
To avoid those headaches, here is our roadmap for today. Introduction and prerequisites, site and mechanical setup, electrical and control wiring, earthing and cable selection, parameters and commissioning, and finally, common mistakes. Let's dive right in.
Section 1. Introduction and Prerequisites.
Look, everyone remembers the VFD and the AC motor, right? But true professionals know you need the whole package. You need your protection devices like your MCCBs, MCBs, and contactors. You also need your power conditioning hardware, so input and output reactors and EMI filters to handle those pesky harmonics. Depending on your application, you might even need a brake resistor. And crucially, having the right power, control, and earthing cables alongside proper cable glands and lugs is a game changer. It totally prevents that uniquely frustrating moment of having to halt an entire installation just because you're missing a 50-cent ferrule.
Section 2. Site and Mechanical Setup.
The crucial point here is managing the physical environment. The ideal location for your VFD has to be dry and dust-free to protect the internal circuitry. It also needs to be well ventilated to manage the ambient temperature and humidity. And you've got to keep it in a vibration-free area strictly away from direct sunlight. Heat is a VFD's worst enemy. If you bake it in the sun or let it choke on factory dust, its lifespan is going to plummet.
When you're actually mounting the thing, whether you're wall mounting, panel mounting, or snapping a smaller drive onto a DIN rail, there is one non-negotiable rule: cooling space. You literally cannot suffocate the drive by packing it too tightly next to other components. You must ensure adequate mounting distance around the unit. Always verify the fan airflow direction so you aren't blowing hot air directly into another sensitive device. And of course, ensure your fastening is completely secure to withstand any environmental vibration.
Now for Section 3, electrical and control wiring. Think of the chronological power wiring sequence kind of like a river of current. You start at the three-phase supply. From there, power flows into your MCCB and optional contactor for protection and switching. Next, it routes through the input reactor to smooth out the line side. Then it finally lands on the VFD inputs, your R/L1, S/L2, and T/L3 terminals. From the VFD, the modulated power exits via the U, V, and W terminals straight down to the motor. And obviously, every step of the way, you absolutely must tie into that PE, or protective earth terminal. So if the power wiring makes the motor move, the control wiring is what makes it smart. This is how the PLC, SCADA system, or your human operator actually commands the VFD. You've got your standard start and stop push buttons, forward and reverse commands, and potentiometers for really fine speed control. But I want to draw your attention specifically to the emergency stop and fault reset. That emergency stop circuit, it's an absolute necessity. It has to be hardwired flawlessly to ensure immediate halting of the equipment. It's about protecting human life and your machinery. Moving on to Section 4, earthing and cable selection. Let's talk about earthing, or grounding. Now, in a VFD system, this actually serves a pretty brilliant dual purpose. First, it ensures strict electrical safety. By properly earthing the VFD, the motor, and the panel, you're protecting personnel from lethal electrical shocks. But simultaneously, it acts as a shield ground. You know, VFDs are notoriously noisy devices. They generate a ton of high-frequency electrical noise. A proper shield ground dramatically reduces this noise, which keeps your sensitive control signals clean and accurate. Okay, when it comes to cable routing, there is a golden rule you have to follow. You have power cables handling high voltage and high current. Then you have control cables handling highly sensitive, low voltage signals. The rule is simple: always route them separately. If you run your power and control cables in the exact same cable tray, the electromagnetic interference from the power lines will induce noise into the control lines, and that causes absolute chaos in your system. And remember, those control cables must always be shielded, no exceptions.
Almost there. Section 5. Parameters and commissioning.
Look, entering motor parameter settings is definitely not a guessing game. You must take the nameplate directly off the AC motor and input these values exactly as stated. We're talking motor voltage, motor current, frequency, and RPM. Setting your maximum and minimum frequency along with your acceleration and deceleration times ensures the mechanical load isn't jerked around or over-torqued. Getting these motor protection settings right is exactly what stops your motor from burning out when things get heavy. Commissioning has to be a highly systematic procedure. First, you need a really thorough visual inspection and wiring check to make sure everything is tight. Second, you run offline insulation and continuity tests to ensure there are no dead shorts. Only then do you proceed to step 3, which is powering on the system and configuring the parameters we just discussed. Step 4 is a trial run without a load, just to verify the motor rotation direction is correct. And finally, step 5 is the load test and final inspection so you can actually watch how the drive handles real-world operation. Finally, Section 6, Common Mistakes to Avoid. You really need to watch out for these absolute project killers. Wrong phase connections or completely missing the earthing can be instantly catastrophic. Loose connections and using the wrong cable sizes, massive fire hazards. We already know poor ventilation will slowly cook the drive's electronics. And routing control and power cables together, well, that's going to give you phantom faults that will take weeks to troubleshoot. And of course, entering incorrect parameters or mismatched motor ratings means your VFD just can't properly protect the motor. A single error here ruins the entire setup. Ultimately, flawless execution is what we're striving for here. Industry leaders like DEVI Automation Solutions, who focus on smart technology, IIoT, AI, and powerful industrial automation, rely heavily on exactly these standardized, rigorous installation procedures. High-level automation only works if the foundational VFD installations are flawless, safe, and built for a better tomorrow. So, I'm going to leave you with a quick question to think about today. Visualize the panels running the most critical processes in your plant right now. Are your facility's VFDs truly safe from these common errors? Is there a control cable lying just a little too close to a high voltage line? Are the cooling fans actually unobstructed? It might be time to take a walk down to the shop floor and inspect your own setups. Thanks for joining me for this explainer, and as always, keep learning and stay focused.